Here's the distribution of defective can openers in a shipment of 400 can openers. And we're trying to decide, is that sample result of 2.75%, is that far enough away from the acceptable 2% level to say that there's too many defects in the shipment and we're going to throw them out? We aren't going to accept the shipment. So if we think about, so I calculated the standard deviation, changed it to percentages, and there's the center of 2%, and then I set up, remember, 68% of the sample of these samples of size 400 will have a defect rate of between 1.3 to 2.7. 95% of the samples of size 400 will have a defect rate between 0.6 and 3.4. And we're just trying to say, is that far enough away from 2 to say there's a problem going on? Well, that's just barely, that p-hat value is just barely over the 1 standard deviation mark. Okay, so to say that there's more than 2% defects, that's what we're looking for, is that percentage, that tail area right there. And that works out to be a pretty small, 0.14. So there's a 14.2% chance that we could get a sample with that high defect rate if the actual defect rate per average, on average, is 2%. So that's a very large p-value. That it's not an unusual value. If you go back and think about the 5%, if we think about 5% being unusual, if an event that the probability of an event happening is less than 5%, we can say it's unusual and not likely if the center is true. And this is a whole lot more than 5%, so we can't say that it's an unusual event. Okay, so that's all we're doing with these p-values. I mean, if you talk about the critical value, what is a critical value here? Just a minute. I'm looking at that z-score table. It says I don't see where we're given the level of significance. I could not be looking at the right page, but even at a 10% level of significance, they're saying 1.28, and we're not anywhere close with that z-score. So again, that verifies that we can't say that the can openers have a higher than 2% defect rate. So I hope that helps.